because some books actually call them the same thing, which really abstractly they are sort of, because they're very similar in concept. But as I mentioned before, threads are normally processes are normally a user level abstraction. Threads are normally a kernel level abstraction in terms of what we're working with. We have processes, and then we have what people call lightweight threads, so they can memorize the differences between the two of them and then go, well, multiple threads can be inside of one process. But isn't a thread a process? When you think about it, if you have a one process and inside the process is only one thread, abstractly a thread is a process, back and forth. But if you want to remember it kind of in a generic fashion, process is always what we're running at a user level. Thread's always what we're running at a kernel level. Nowadays we have a one-to-one mapping. So if we have a one-to-one mapping, we could call that process a thread, we could call that thread a process. Isn't it the same thing in terms of its naming convention? So let's talk about mapping then. So we have multi-threaded models, we have threading issues, p-threads, Windows XP threads, Linux threads, and Java threads, and then multi-threads. So here's the concept of single and multi-threaded processes. Remember that thing I stopped at today, and it was a big old line, and I said it's memory. I said processes are memory abstraction, and inside the process we had the code, the stack, the heap, the text, and all that stuff. So we have the same thing. So we have single versus multi-threaded processes. Threads live inside of processes. So a thread is a thread of execution. A process is a running program on the computer, which is why I always say user mode has running programs. Kernel doesn't normally run programs. Users run programs, but kernels run threads because we have to execute something. And the CPU scheduling is really process scheduling, but it's really thread scheduling. Think about it. So here we have one thread of execution inside of one single process. Here we have 3 threads inside of one process. Why do we want that? Well, if we were to take a process, break it out into smaller pieces and schedule it all together, we're going to get more processing done, which is kind of interesting. So if we can create multiple threads inside of one process, and then we have multiple, three things working for us instead of just one from a kernel perspective. So it makes things run faster. So people do multi-threaded to make their programs run faster. If the entire program is running in one thread, you're getting one single process abstraction, one thread that's running. If you have multiples in there, you're getting more CPU time because you own more threads. And the CPU's got more threads. Benefits to multiprocessing: responsiveness. It's a lot more responsive. The program itself is getting more power. There's 3 of them instead of 1. Resource sharing, economy, and utilization of MP architectures. Yeah. So you're utilizing the architecture a little bit more, especially if you look at different types of operating system designs for different types of hardware. Some of them want multiple threads because you'll get more processing done. And then economies of scale. So we got user threads and we got kernel threads. User thread is like a process. We have thread management done by the user level thread libraries. That's the P threads, or POSIX threads in Unix. 3 primary thread libraries. POSIX is the Unix. There is a Win32 thread and there's a Java thread, which is why I said you could do that first assignment in Java if you'd like. You can create a shell in Java. Java supports threads. This is kind of hard to do. The Win32 threads, there's no user level control on it. But you still have threads in in Windows. In Unix, you have POSIX threads, or P threads is what most people call them P threads. And you have user level control over it. So it's a little bit different. So you can create multi-threaded programs in Unix, but you can't do that in Windows. But Windows supports threads, but only from an operating system perspective. User mode can't create Windows 32 threads. So this was user perspective of threads. So user threads. Now we have kernel threads, supported by the kernel. Everybody's got kernel threads. Windows, Solaris, Linux, Unix, Mac, everybody's got threads. Why does everybody have kernel? Everybody has kernel threads. Because kernel is, we have a kernel on a Windows system the same as we have a kernel on a Mac or a kernel on a Unix box. And the thread is the form of processing that's being performed by the CPU. So it's all thread based. So we have multi-threaded models. And there's been a lot of experimentation with the multi-threaded models, and this is another source of confusion for a lot of computer science students when they go, what's this one-to-many, one-to-one, many-to-one kind of concept? So I'll kind of give you some examples of how this would work. In the many-to-one, which means there's many threads mapped inside of one process. So we have many user-level threads mapped in terms of a single kernel thread. So when we talk about the mapping, we're going user thread to kernel thread, or kernel thread to user thread. So one to many is one user, many to one is many users inside of one kernel. One to many is one user inside of many kernels. It's the opposite. So many kernel threads, user level threads mapped inside of kernel level threads. This is what we get with Solaris and GNU portable threads. So when you're actually creating threads, you're only getting one single kernel thread, even though you have, because only one of them is running at a time. The parent and the child. Parent waits for the child, child executes, goes back to the parent, vice versa. Many to one, in terms of the model, we have these are the user threads, and they're inside of one kernel thread. So with this type of mapping, it doesn't really matter. I mean, we can just have many different user level threads inside of one kernel thread. We can make the kernel level thread bigger. It houses many user threads. We can get all those threads being processed from a kernel perspective. Just keep in mind, user level and kernel level have different thread abstractions. And when processes run at user level. One-to-one. Each user thread maps to one kernel thread. That's everybody. That's Linux, that's Unix, that's Solaris. Everyone's doing a one-to-one mapping because it's easier. We're not going to lose any threads, and it's just simplified. But there's been a lot of experimentation with the other different models. There's no law that says it has to be one-to-one. Somebody might come out with a better model in the future that does multiple to one. Well, think about it. If we had all multiples and the kernel thread was running, we could split the multiples out over different processors. Single processor unit, one-to-one makes more sense. Multiple processors, multiple CPUs, maybe multiple threaded patterns would make more sense. Because then you can spread the work out among multiple CPUs from a kernel perspective, which means you're going to have more than one kernel thread. Here's a one-to-one model where we have one user thread that's associated with one kernel thread. That's our typical model that we're seeing today. It's easier to understand. A many-to-many model, allows many user level threads to be mapped to many different kernel level threads. Maybe for multiple CPUs that makes a lot more sense, because then we can have many different threads running. We want more kernel threads if we have more CPUs, because then we can schedule them off differently. If everybody's inside of one kernel thread, it's only going to run on one processor. So allows operating system to be create a sufficient number of kernel threads, kernel threads. Solaris prior to the version 9 Windows NT with a thread fiber package, older versions of Windows were supporting this model. A many-to-many model where we have many user threads that are mapped to many kernel threads. That's going to be fastest model for multiple CPUs. Single CPU doesn't really matter, one-to-one works just fine. So then we have a two-level model, similar to the many, except that it allows the user thread to be bound to a kernel thread. And examples of that are going to be like some of your variations of HP Unix, UX Unix, Solaris is in there too, some of the earlier versions. Here's our two-level model picture where we have, kernel thread, user thread, and we can basically map them so we know which one's going to which one. So Threading issues. Okay, so we have the semantics of the fork and the exe system calls. Many different varieties of exec. Some people won't use an exec, they'll use a fork. An exec is sort of like a lightweight fork. It actually doesn't create all the same overhead. We have the thread cancellation process, signal handling between the different threads, thread pools, thread-specific data, and scheduler activations. How are we going to schedule all of these threads to run? So let's take a look at the semantics of the fork and the exec. Does fork duplicate only the calling thread or all threads? This is one of the biggest problems in terms of putting multiple threads inside of a process. What are you going to get? If the parent has multiple threads, which one of the parents or which one of the threads are you going to put inside the child? So there's no answer to these questions. These are just problems that come up in terms of the semantics. This is why, this is why most operating system developers have gone one-to-one. The mapping is just ridiculous in terms of its complexity. What about thread cancellation? How are you going to cancel one thread inside of that process, instead of the multiple processes? So terminating a thread before it is finished. Two general approaches here. Asynchronous cancellation terminates the target thread immediately, or deferred cancellation allows the target thread to periodically check if it should be canceled. Signal handling is probably the most difficult to program with. Signals are used in Unix to notify processes. We don't really send too many signals in Windows environment. When you press Control Alternate Delete, it is a signal. Brings up Task Manager. And then when you press on one of the items in the Task Manager, the running programs, and you select the delete, it sends a kill signal to the processes. So it's run through the Windows GUI interface. You actually do have signals. Actually, you can press Control C, usually, in the DOS prompt to control break something. Control pause, C. So you can terminate, you can do very limited things, but you can actually generate signals. So signal handlers use to process the signals, and the signals generated by particular events that might occur, and it's delivered to a process, and it's overhandled. So options here: deliver the signal to the thread to which the signal applies, deliver it to every thread in the process. How are you going to know which one it's supposed to go for? Which is kind of confusing. And then deliver the signal to certain threads in the process, but not all the threads in the process. And then assign a specific thread, this should say thread, to receive a signal for the process. So signal handling gets complicated as well in terms of the mapping. So it's a one-to-one makes a lot more sense. And then we have thread pools. So create a number of threads in a pool where they all wait for work. So instead of going one-to-one and you're creating a thread, having it do some work, you just have a thread pool out there. Advantages: usually slightly faster to service because you don't have to wait for one to be created, it's already created using an existing thread. And then allows the number of threads in the application to be bound to a sizable pool. So you can control how many threads are going to be bound to the process. So you can figure out, well, how to better control them, which one you're going to use, which one you're going to kill. And then we have this concept of the thread-specific data. So it allows each thread to have its own copy of data. So each thread has its own data, which means it doesn't necessarily have to share the data. Useful for when you don't want to have, do not have control over the thread creation process, especially when using a thread pool. So scheduler activations, we have this thing called an activation record, or activation records, which are the instructions that are going to be performed by each one of the processes. And these ARs, or activation records, are stored on a stack structure inside of the process space. So remember that little thing that said stack, and on the other side it said heap, and the stack was growing up into the heap, and I went through that last time. Those stacks are holding what's called the activations, or activation records. And so we can schedule the activation records within each one of the processes using the stack that's associated with the process. So with both the many-to-many and the two-level models, it requires communication to be maintained for the appropriate number of kernel threads allocated to the application. So then we have to keep track of which kernel threads are allocated for each one of the activations so it can be scheduled properly. And then it provides upcalls So you can have an upcall, which is what it's called. It's a communication mechanism from the kernel to the thread library. To upcall to see which thread is going to be to run next. And then the communication allows for an application to maintain the correct number of kernel threads as well. So just know that we have the scheduler activations as a concept. We'll see that with activation records and scheduler activations when we looked at CPU scheduling coming up. So pthreads, we keep calling it pthreads, a POSIX standard. So it's the API for creating and synchronizing threads, which is what we're doing when we program with threads. And so the API specifies the behavior of the thread library, implements it using a library API, which is what you're going to use inside of C if you program it in C. So, common in Unix operating systems, Mac OS X. So. Windows XP threads. Well, it implements a one-to-one mapping. So each thread contains a thread ID, a register set, a separate user and kernel stack, and then private data storage area. So if you go into the task manager, you see processes that are running, you see user level and you see kernel level processes in there, usually identified by the user. Each one of them actually has an ID next to it, so you can actually kind of look at that. So we have the register set, the stacks, the private data known as the context of the thread. And then we have the primary data structure itself for the thread, which includes execute thread block, kernel thread block, and thread environment block. So, very limited user control, however the abstraction does exist. Windows definitely has thread libraries associated to it, and it is a one-to-one mapping. So Linux threads refer to them as tasks rather than threads. So we have a task, which is kind of interesting because we have task manager or task scheduler in Windows. So it's kind of using the same terminology. The thread creation is done through the clone system call, and clone allows a child task to share the address space of the parent class or parent processor task. Java threads, kind of interesting. They're managed by the JVM. Actually, every running class is a thread. So instead of every running program, it's every running class. So the classes themselves have inter-process communication and they share information back and forth, which is kind of interesting. It's all controlled by the security manager. So you can set a security file to give one class access to another class to communicate back and forth. You can put restrictions and things on that. So they can't open and close files. Or one process can, but the other one can't. Different things that you can do with that. So they're created by extending the thread class and implementing runnable interface. So you just use the keyword runnable and it makes it a thread. So it gives you interface, gives you access to the running class as it's running. So the Java thread states, as we're looking at here, very similar to the thread states of a Unix system. So we are new, then we start, makes us runnable, and then we get blocked, and then we die occasionally. And we're all done, exits. Don't really have to know anything about the Java thread states, just know that there are different states to every thread that runs, because it has to transition between different states. If it